Hello and welcome back to another episode of Math with Sohn. Today, we're going to be doing some 2D motion. I'm going to go a little bit slower. That way, hopefully, we can all just pay attention and understand exactly what's happening. So we have an astronaut stands on the edge of a cliff in the lunar crater and throws a half-eaten Twinkie. That's fun, trademarked. With an initial velocity of 5 meters per second horizontally. So if it is horizontally thrown, anything horizontally thrown, even though it has a velocity of 5 meters per second horizontally, the VI for Y is 0 meters per second. It's no different than it is dropped, okay? The floor of the crater is 100 meters below the astronaut. So this thing's going to have to go from like a cliff, and then it has to fall potentially 100 meters down, all right? What horizontal distance will the Twinkie travel before hitting the floor of the crater? So we want to know how far will it go horizontally if it is thrown. So this is the Twinkie. It is thrown this way horizontally, but then it's going to curl down and it's going to fall, okay? And it won't go that far horizontally. That was just me drawing. All right, so we have to establish how to do this. Currently, we don't know the time. We do know the gravity on the moon is negative 1.63 rather than gravity on Earth 9.81. So what I'm going to do is I'm going to write down the formulas. We either can use delta y is equal to VI for y times time, 1/2 gravity t squared. And then if you try that one and it works out, great. If you try that one and it doesn't work out, then okay, that's not the problem, not the formula to try. I'll show you later on one of the problems I had to scratch out. It was number 2. I had to scratch out 2 equations just to be able to get the right one. How far did it fall vertically? Well, it fell vertically 100 meters. So we can fill that in. What is, and by the way, notice how I wrote down 100 meters. If you put positive 100, it's not going to work out as nicely. The initial for y is 0 because it was thrown horizontally. There's no up and down velocity in the beginning. So this would be 0 times time. And then plus 1/2 gravity. The gravity on the moon is 1.63, and 1.63 for the moon, even though it's the moon, is still directed downward, times squared. So here, even though we have a t and a t squared, that 0t is going to cancel, leaving us with negative 100 is equal to 1/2 of, let's see, 1/2 of 1.63 is negative 0.815 t squared. You divide by the negative 0.815 and square root when you get that answer. You get 122.69 is equal to t squared. And that means the time is equal to 11.07 seconds. Not an answer, but it is definitely required. Normally, you're going to have to find time at some point. If it's not given to you, you're going to need time. Let's just put it that way, because time is the only thing that x and y both have in common. So now we have to figure out how far horizontally it will go. We need to get this delta x over here. Well, delta x is the exact same formula. It would just be VI for x times time plus 1/2 gt squared there. But for horizontal things, it doesn't have a acceleration, so that part goes away. So that means that our delta x is just going to be the initial velocity for x. But what was the initial velocity for x? 5. Whatever the horizontal velocity is, it will stay that for the entire duration. We plug in our time that we just found, and we get a delta x of 55.38 meters. Excellent. That's the time. No, that's the distance that it would go horizontally. So 55.38 meters. Beautiful. All right. Next one, we got a baseball player leads off the game and hits a long home run. Congratulations. The ball leaves the bat at an angle of 30 degrees from the horizontal with a velocity of 40 meters per second. We need to know how far will it fly horizontally in the air, and assume that the height that it, gets in contact with is also negligible compared to like the home run thing. So that's nice. We're assuming that it goes from the ground to the ground essentially. So in this first problem that we have an angle, we need to draw a triangle for that angle. 30 degrees, and it left with 40 meters per second. So if it gives you these two essential things, I always recommend using that to find your VI for Y. Remember, that is 40 sine of the angle, because it would be the opposite that we're looking for. So 40 sine of the angle ends up equaling 20. I didn't need a calculator for that. Well. And then here for our VI for X would equal 40 cosine of the angle, which that ends up equaling 34.64 meters per second. So it's going a little bit faster horizontally than vertically. It's going up by 20, but over by 34.64 meters per second. Okay, so now what formula do we need to use? Well, here's where I struggled, you can tell. Like I started with this one and I was like, no, don't want it, didn't want it, didn't want it. And then actually went back to one of them because I was like, I could have used that one. So everybody struggles with maybe which formula. So write down one, and I encourage you to write down the formula and then plug it in, because then you make less mistakes, and mistakes are brutal. Why make a mistake when you do all the other physics right? So in this case, delta y is equal to VI times t, 1/2 gt squared. We're going to have to solve for time if we do this. Now this one actually has two options. You could calculate the time it takes to get to the top, and then you could like double it, right? But in this case, I'm just going to use this one formula because it bounces off of this idea where we have a delta y. When it starts on the ground and lands on the ground, or if it starts at the bat and lands at the same height as the bat, that height difference is 0. We do have an initial velocity for y of 20 times time, don't know the time, plus 1/2 of negative 9.81 t squared. We end up solving for time here. You get 20t minus 4.905 t squared. Now you could use the quadratic formula here, but I recommend if you only have a t and a t squared with this 0, then all you have to do is technically factor out a time, and you get 20 minus 4.905 t equals 0. You get 2 times. Time equals 0, and time would equal whatever 20 divided by 4.905 is, which ends up equaling 4.07. Well, why does that make sense that it would be on the ground at a time of 0? Well, that would be when it was hit. Like the time it was hit, it was at the same height as it landed. And the other time, the more important time, would be the 4.07 seconds. All right? So with that in mind, we got the 4.07. Now what do we need to do with it? We need to figure out how far will it go horizontally. So for part A, how far will it go horizontally? Delta x is equal to VIx times time plus 1/2 gt squared. But again, remember, there's no gravity for x, so that 1/2 gt squared is going to cancel out. Plug in the time, plug in our horizontal velocity, 34.64 times 4.07. You get an answer. That answer is 141.2 meters. All right. Part B. How high will it travel to its apex? So from here, you got options. I would recommend you could take this time and cut it in half because it will be at the max height at that time, and then you could plug it in. That's one option. The other option that you could do is you could be like, well, V final squared equals V initial squared plus 2a delta y or delta x, but we want to know how high, so it's a delta y scenario. On the top, your final for y is 0. Our initial for y is still 20, so it'd be 20 squared, 2 gravity, delta y. You just solve for your delta y. So you end up with 0 is equal to 400, and then this would be 2 times g, which would be plus 2 times negative 9.81 delta y. If you solve for y here, subtract 400, divide by like that 19 point something number, you end up with a delta y of 20.38 meters. Okay? So not too bad, and one of the ways that you could get there. All right? Number 3, a punter in a football game kicks a ball from the goal line of 60 degrees from the horizontal of 25 meters per second. So we got 25, we got 60 degrees. We need to probably find our initial for y, which would be 25 sine of 60. If you do that, you end up with 21.65 meters per second is our initial for y. And then over here, we'd have 25 cosine of 60 degrees, which ends up equaling 12.5 for our initial for x. Okay? So anytime you can find your initial for y and your initial for x, just get it out of your calculator real soon. Make sure you're not in radian mode. You need to be in degree mode. For those of you that have still not upgraded, well, technically downgraded the scientific calculator, please do so, because I've had so many people get things wrong that shouldn't. Anywho, what is the hang time, total time in the air? Well, let's think about that. For part A, I'm going to go with the easiest equation. Maybe it'll work. Maybe it won't. If we want to know the time that it was in the air for, excuse me, assuming it goes from the bottom to the top, like from ground to ground, then the final at the top is 0. Will equal an initial, which would be for y, 21.65, not for x, because we're not going to use a horizontal to figure out how long it goes up then comes down for, minus 9.81 times time. Now, when I solve for time here, what is this time going to represent? This time will be the max height time. And if I want to find the total time, I could just double it. Not the only way to do this problem, but it is a little bit quicker. So if we solve for time here, it ends up equaling 2.2 approximately. And if you double it, that's your half time, if you double it, you get a time of 4.41 as a total in seconds. All right. The other option that you could have done could have been delta y vi times time, 1/2 gt squared, just like that problem we did up here where we set it equal to 0 and solve for time. You could do the exact same thing. You could set delta y equal to 0, you could factor, you could solve for time that way. I'm just showing you a slightly different way to do it this time because in some cases, this is the only way to do it. In other cases, this is the only way to do it. But in some, you get 2 options. All right, for part B, how far down the field did it take to land? So we have a delta x is equal to vi for x times time, technically plus 1/2 gt, but that 1/2 gt squared does not apply because it does not have acceleration for the x. X is what we're looking for. Delta x will equal vi for x, which is 12.5 times the 4.41. You get a delta x of 55.17. So this was a good 2 examples mimicking one another back to back. All right. A movie stunt driver on a motorcycle speeds horizontally off a 50-meter cliff. Okay, so he's going horizontally. How fast must the motorcycle leave the cliff top if it is to land on level ground below a distance of 90 meters from the base of the cliff? I got to read that one again. All right, so he's 50 meters high. So that's important. He's 50 meters high. He's riding a motorcycle. Motorcycle. Off of a 50-meter high cliff. He wants to go 90 meters over. So in this case, that 90 meters, he needs to do that in a certain amount of time. All right? And I know that if he's going horizontally, the initial, he's going all horizontally, the initial for y will be 0. Okay, so the vi for y is 0 because he's only going horizontally. His initial velocity for y has got to be 0 meters per second. So that means he has to fall 50 meters. So that means that we have negative 50 is equal to our delta y. Because he started up here, he went down there. So delta y will equal our initial for y times time, 1/2 gt squared. So we have negative 50 is equal to an initial for y, which is 0 times time, 1/2 negative 9.81 t squared. We have to solve for time. If we solve for time here, 0 goes away. We divide by the 4.905. We square root. You end up with a time of 3.19 seconds. I'm assuming that math, just going through that quickly, is not a big deal. If I'm wrong, I'm sorry. All right, that's the time. So we have a time of 3.19 seconds. That's how long he is going to be falling in the air for, going down and hopefully splashing down at 90 meters away where there's something soft. All right? So with that in mind, our delta x we know is 90. So our delta x is equal to VIx times time, 1/2 gt squared. But again, for horizontal, no gravity. 90 positive because he went to the right. VI for x, we don't know it, but we know our time is 3.19. When we solve for our VIx, we get our answer. VI for x will equal 28.18 meters per second. All right, moving right along. Hopefully it didn't bleed through. It did a little bit. You're piloting a helicopter, which is rising vertically at a uniform velocity, 14.7 meters per second. When you reach 196 meters, you throw out a water balloon. The water balloon is thrown horizontally with a speed of 8.5 meters per second while the helicopter is still traveling upward. Think about what this means. What it means is that because you're going up by 14.7 meters per second and you throw something out horizontally at 8.5 meters per second, you actually have a velocity for y of up by 14.7 and a velocity for x initial of 8.5. All right? When does the object reach the ground? We have a velocity for y. It is how high up above the ground? 196. So we have to fall 196 meters. Well, this balloon does. So this delta y is going to be negative 196. Delta y equals VIy times time, 1/2 gt squared. It is by far the most popular formula, that one with the delta y or the delta x. Negative 196 equals positive 14.7 because we were going up by 14.7 meters per second times time plus 1/2 negative 9.81 times time squared. In this problem, we have a time and a time squared and a negative 186. This would be a quadratic formula problem. So this is a quadratic formula problem. You can use your graphing calculator if you still have that. However, we do need to be able to do the negative b plus or minus the square root of b squared minus 4ac all over 2a. Got to be able to do that on a very random problem. And if we do that in this case, we get 2 times, but the only time that matters is a time of 8 seconds, which is a very pretty number, which means this technically was factorable, perhaps? Who knows? All right. When does the object reach the ground? Done. What is the overall velocity? Not speed, but velocity when it hits. Okay, so if it's velocity, I'm going to recommend just doing speed. So in this case, we have it thrown horizontally. So when it lands, it's going to do this sort of number. When it lands, it is still going to be going 8.5 meters per second to the right. But it will be going faster than 14.7, most likely, when it lands, because it had to gain speed on the way down because of gravity. So we still need to get that final for y. So the way we get the final for y for part B will probably be doing something like this. V final squared, V initial squared, plus 2a delta y. That's one option. That is definitely an option. You could do that, which means we can do part B even if you get part A wrong. All right, that's important. If you decide to use your answer from part A, then you could use this formula. V final, V initial, gravity times. So both will get you the answer. This version will get you the answer even if 8 seconds is wrong. So I'm going to do this one even though both will work. V final is what we're looking for. For y, initial was 14.7. 2 times negative 9.81. And then we would plug in a negative 186. You end up with a V final for y of 63.78 meters per second, which is technically negative. Your formula will not tell you it's negative if you use this one because you're square rooting, but you have to know that you're going down. So if this is 63.78 and this is 8.5, you have to do the Pythagorean theorem to be able to get that hypotenuse because it's actually going that way. So 63.78 squared plus 8.5 squared will equal c squared. If you solve that, you get a true velocity final of 64.34 meters per second. Now, technically, this is a speed. If you want the velocity, all you would have to do is find that angle, okay? So sometimes it says overall velocity, not speed, but velocity. That means that you just have to find the angle, and the way you find that angle is you just take tan, sine, or cosine with the appropriate opposite adjacents or opposite hypotenuses. I'm using tan, so I need to use opposite over adjacent. And if you do tan -1 of opposite over adjacent, tan -1, 63.75 divided by 8.5, you end up with an angle of 82.4 degrees. Okay, so now you found the velocity. Once you find the angle, now you have the direction, now you have the velocity. All right, last but definitely not least, a ball is launched at 57 degrees to the horizontal at 15 meters per second from an elevated position. It travels in a parabolic trajectory and lands on level ground, which is 35 meters below the launch point. How far did the football travel before hitting the ground? What is the maximum altitude? So for part A, actually, let's draw a picture here. We got a cliff that is 35 meters high because it said 35 meters below the launch point. It was launched at an angle of 57 degrees at to the horizontal 15 meters per second. We need to find our initial for y and our initial for x. Your initial for y, as always, is going to be 15 sine of 57, which is 12.6 meters per second. Your initial for x, as always, well, maybe not always, but as most of the time, 15 cosine of 57, which is 8.17 meters per second for your VIX. All right, so those two things are there. Now we have information available that we can use. How far did it fall before hitting the ground? I think we're going to need the time, and I'm going to get the time with, again, my old faithful delta y, VI for y, time 1/2 GT squared. So delta y is not 0. It's also not 35. It is -35 because it went down by 35 meters before hitting the ground. It is going up by 12.6, not down. In some cases, it could be down. Maybe you kick down instead of up. 1/2 -9.81 t squared. This, again, is a quadratic formula question. Because you have a time and a time squared, you might want to set it equal to 0 and arrange it in a way that is easier for you. Which means that your C, your A, and your B are a little bit easier to identify, but you would use the quadratic formula. To save time, you would use the quadratic formula, and you end up with a time of 4.24 seconds. Not the answer. We want to know how far did it fall or travel before hitting the ground. Well, for part A, we would need to be able to figure out the delta x because it went, from this cliff, it went up and then it went down. How far did it go? I'm assuming we don't want to actually know the hypotenuse because that wouldn't make sense. How far did it go from the base of the cliff? So delta x would equal your VI for x times time 1/2 AT squared. Again, does not matter. So delta x would equal 8.17 times 4.24, which is, I don't know why I'm multiplying it. I've already typed it in my calculator. 34.64 meters. Part A done. Part B. All right. What is the maximum altitude? You got options for the maximum altitude. You cannot take half of the time, though. So actually, that really limits the options. So you can't just half this time because it would be the half time from here to like this spot, but it took some time to go from that -35 down. So it's not just a half time increment to get to the max height this time. In this case, I am going to use this formula. And the final velocity for y at the top will be 0. The initial velocity for y is the initial velocity as before. Gravity is your a, negative 9.81, and then you just solve for your delta y. So if we do that math, you end up with some numbers, and I just typed it and stored it in my calculator. You would subtract the 12.6 squared, then divide by the 19.62, I believe, and you get a delta y of 8.09 meters. Be careful. That is delta y. That is not your max height. That is delta y. We were up 35 meters. We went higher than that by 8.09. So if we went higher than that by 8.09, that is our change in height. 8.09 and the 35 end up equaling in total max height of 43.09 meters high. Okay? Make sure that you recognize delta y doesn't always tell me my max height. It tells me my change in height. All right? That's going to do it for this one. Until next time, everybody, stay positive, and I will see y'all later. Bye.